Okay, so we'll continue. I think today will be the last lecture that we will have on regression. So, so last time what we did was we continued kind of with the review of linear algebra and really concentrated on, the SVD. So SVD is a very important decomposition. It pretty much tells you all there is to know about a particular matrix. It exists for any matrix. And it is this decomposition U sigma V transpose. And we talked about the full SVD and also something called either the thin or the reduced SVD. But also, you can actually truncate the SVD at any K. So you can, if the full SVD is U sigma V transpose as given over here, right? The thin SVD is sometimes called this U hat, which takes where m is greater than or equal to n, and you take the first n singular vectors, U hat, sigma hat, V hat transpose. But you can actually truncate it at any K. So you can just take U1, U2, for example, or U1, U2, U3, and then take the corresponding singular values. They are, of course, ordered in decreasing order, and then also the corresponding V's. And that is sometimes called the K-truncated SVD. And one of the really nice properties of the SVD is that actually that gives the best rank K approximation to the given matrix, right? So for example, here, if you have a given matrix A and you want to find out the best rank K approximation of this matrix, then you can basically just take, UK sigma K VK transpose, where UK is m by K. Maybe I should actually write it over here. Sigma UK belongs to R m by K. Sigma K belongs to R K by K. And VK belongs to R n by K. Okay. And that gives you the best singular value, best truncated, best rank K approximation. Okay. Then we went back to least squares regression, and we saw that least squares regression, if you analyze it using the SVD, it's actually just the orthogonal projector onto the range space of the design matrix, which is X transpose, right? Which is made of the training samples. So today we will kind of talk a little bit more about regression, some of the issues that there are with just doing regression as we've talked about it, for example, least squares regression, and talk about something that is really needed to make the regression better, which is regularization in regression. And there we look at a particular way to regularize, which makes the prediction better. And we will see that we can actually analyze this method called ridge regression quite well by looking at the singular value decomposition. Okay, so reminder that regression is, I have training data, xi, yi. Xi is d-dimensional, d features, the y's. Since we are talking about regression, these are real numbers. And linear regression is basically taking a linear combination, which is W naught plus W1 x1 plus W2 x2 plus WD XD. All right, it's the prediction for a new unknown X value. Okay. Now, even though I've called it linear regression, sometimes you can kind of do nonlinear regression using this scheme. So let's talk about a particular example, which I will use to motivate the need for regularization. So let's think about polynomial interpolation or polynomial fitting. Okay, and we'll talk about, the simplest case, which is univariate polynomial fitting. Okay, what do I mean by that? Okay, so in this case, what I will say is that, we actually have just one single value of x. Okay, so my d is equal to 1. Okay, but what I will do is I will actually derive some nonlinear features from x. So I will take x and I will map it onto something called phi of x. Okay, so I'm going from actually R D. Okay, and in this particular case, it is D equals 1 to R, let's say D prime. So phi of x is of dimension D prime. Okay, and in particular, the way we can think about polynomial fitting is to think about phi of x as the monomials. So x square, x cube to x to the power d. Or x to the power m. Let me not reuse. Okay. I guess I've used d prime. So in this case, m is equal to d prime. Okay. So if I want to do linear prediction, so polynomial fit at x, we'll see is equivalent to linear regression for phi of x. Okay, so let's think about what linear regression of phi of x is, right? And let me call that as z. So if I say that this vector is z, okay, so remember what is linear regression for a vector z? It is w naught plus w1 z1 plus w2 z2 plus w m zm. Okay, and in this case, my z, as I've said, the components of it are the power. So the ith value, the ith component of this vector z is actually x to the power I. So I have w naught plus w1x plus w2x squared plus wmx. And many of you might have seen this problem before, right? So what you are trying to do is you're trying to fit a polynomial to a univariate polynomial to a given data. So this is a technique that is many times, you're using linear regression, but you're actually doing a nonlinear fit because the different powers of x are nonlinear in x, of the features of x. So this is not that uncommon, and you can actually apply it even when x has dimension greater than 1. So you typically take, you are given RD and you can map it onto RD prime. Typically, D prime is much, much greater than D. So for example, here M is could be much greater than 1, right? And you basically have, the way we denote it is, you take X and you do a map with a nonlinear map called phi. And then we'll do prediction using phi of x. Okay, So let me show you some examples, okay, of polynomial fitting. And let me share my screen. Okay, so you guys can see my screen. And so this is an example from this textbook by Chris Bishop. Okay, hopefully all of you can see it. Okay, so, here's an example that, you might want to recognize digits. That's a classification problem. But here is the problem that we are talking about, right? So here, think of, a particular X. So X is given over here, right? And this is the value that you want to fit, the y-axis, right? So you have basically X, comma, and then you have, you have the value at x1, you have a value at another point x2, you have a value at another point x3, and so on, right? But for a particular x, what you want to do is you want to fit a polynomial, right? So y in this case is a polynomial, and you can see that is exactly what we are talking about. And it is linear regression on phi of x, where the ith component of the vector phi of x is x to the power I. Right? And over here, in the green line is shown like the kind of fit that you would kind of think is natural for this data set, right? Notice that this fit does not exactly pass through all these points, okay? But let's see what happens when you try to vary capital M, okay? So you, of course, we can do least squares regression. This is just the sum of squares error function. And now think about what a zeroth order polynomial is. Well, a zeroth order polynomial says that I'm just fitting things by W naught. Okay, and that's it. And you might say, okay, what should the value of W naught be? And if you do the math, it'll end up being the average of all the Y values. But it is just this red line is the fit that you would get if you just take M equal to 0. And you can right away say that, hey, that's probably not a very good value of M to take, right? If my goal is to fit this set of points. So then you can say, okay, I can increase capital M. And if I make capital M equal to 1, then I get a straight line. And this is the straight line you'll get if you fit it to this set of points. Now, how many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. Okay. So you get that. That again seems, it's better than a constant, but still you can visually see that it's not very good. So let's try to increase M, and this time to M equal to 3. And you can see that it's actually now kind of getting better, right? So M equal to 3 is this value, right? Now from the theory of polynomials, you know that a third degree polynomial can have kind of 3 roots. And you can see that, there is going to be one root, or the value of the polynomial 0 here, 1 here, and then 1 over here. Okay, so the polynomial will kind of oscillate, right? Because there are these roots. And then you can say, okay, obviously the fit got better as I went from M equal to 0 to M equal to 1 to M equal to 3. Let's try to make it even better. Let's try something, well, much higher, 9th order polynomial. Oh, and look at this fit. Now this red line is the fit. Now anybody wants to kind of say whether this is a good fit or not?
Yeah, that's terrible.
So remember, our goal is prediction. Okay, if it was so one of the things that you will notice, so the reason I think Hormuz you're saying it is terrible is that, it actually just oscillates very wildly, right? But note that at all the points that were given in the training set, it actually passes exactly through them. Okay, but remember, our goal is not polynomial interpolation, which means to fit the polynomial exactly at that point. Some of you might have taken like a numerical analysis course, and there you might actually have used polynomial interpolation. And clearly, if there are 10 points, like for example, if there are 2 points, you can fit them exactly by a line. If there are 3 points, you can fit them with a polynomial of degree 2. And in general, there's a theorem that says that if there are m plus 1 points, you can fit it with a polynomial of degree m. That means you'll make 0 error. But remember, that's not our goal here. Our goal is to be able to predict at a new point. Let's suppose an x over here. It does fine over here, right? Okay, and even if you do polynomial interpolation, by the way, this is not good. So people do other things like piecewise polynomials. So what is happening over here? Okay, what is happening here, and this is the first time you're seeing this, and this is a big problem in machine learning where you are trying to overfit. You're trying to fit too well to the training data. But remember, our goal is what's actually called generalization. Yes, you want to fit to the training data, and where you want the training data to be representative of the final task, right? But the goal is to predict at some new point. Okay, so if you look at so typically what you can do is you can divide your data, or you have like a training set and a test set, right? The training sets, what happens is in this place, as you increase the degree of the polynomial, you can see that it decreases. Okay, sorry, the training set is in blue, and you can see it as decreases. And like I said, a 9th degree polynomial will fit these 10 points exactly. So the training error actually decreases to 0. Okay, but the test error, which is a new point, when I try to predict on this, the training error kind of declines, but then it shoots up. And that's this phenomenon called overfitting. That means you've overfit too much to the training data. Your predictions will actually not be good for a new point or the test data. Okay, and like, why is it happening over here? If you look at the polynomial coefficients, you'll see what might be happening, right? So with m equal to 0, I had a coefficient of 0.19, right? And I'm guessing that that is the mean of all the y values over here. With m equal to 1, you see that you have coefficients of the order of 1. M equal to 3, the coefficients are actually kind of slightly higher, right? It's 25 and 17. But look at what's happening with m equal to 9. The coefficients are actually becoming really big. And the reason they are becoming really big is what's happening is that some values become very large and some values become very small. So that's why you'll see that, you have very large positive values, very large negative values, and they somehow cancel to give you 0 error at the training data, on the training data. Okay, so one symptom of overfitting is that my coefficients, right, are actually getting very large. You can think of that as that your predictor is actually getting a little bit more complex, right? And that's one, in this case, it manifests by these very, very large values, okay? So what do we do then? What should we try to do, right? Well, remember that so far, we talked about the error on the training data. This was the error on the training data, and we are looking at least squares regression, so we take the squared error, and we are trying to decrease it. But we've seen that just decreasing it isn't the best idea because you can overfit, okay? the model is becoming too complicated and it's trying to overfit. Simple model is better. In this case, what happens is that this manifests in the coefficients becoming too large. So then what you can then do is you can say, okay, my goal is not to just fit the training data, right? I'm actually going to do something called regularization, which means that I'm actually going to penalize my coefficient, two large values of my coefficients. So this is called, this particular regularization, where this is the 2-norm square, is the ridge regularization. And lambda is a parameter that kind of trades off between the fit to the training data and the complexity of the model. Okay, so for example, if lambda equal to 0, we'll be back to our previous case where we are just fitting to the training data, and we might get too complicated a model, we might overfit. On the other extreme, if we take lambda close to, let's say, very large, so in the limit, we take it to infinity, right? Our W will be, in some sense, constant or even 0, right? Because if I take this to infinity, what I will get is that, W should be actually all zeros. And that's not a good predictor. So typically you want lambda to be good. And ideally what you want is that, over here, we had this M. If you kind of look at a value of lambda over here, typically that's what will happen, that when you have too large a model, it'll be too large a lambda. It'll be a very simple model. Your training as well as your error will be high, test error. As you then start decreasing lambda, your test error will keep on declining. But then as you make your lambda close to 0, you will actually overfit and your test error will start increasing. Okay, so let me now stop sharing the slides and move back to, I see. So sorry, I'm just looking at the chat, and I think Prachi, you kind of foresaw what I was going to say, and yes, this is struggling from overfitting. Okay, so let me go back to my. Okay. Okay, so now what we will do is we will do ridge regression. Okay, so I'm going to contrast it with just the linear regression that we did. So let me talk a little bit about ridge regression over here. So let me write it over here, ridge regression. Okay, so the goal in ridge regression is to minimize a combination of fit and regularizer. Okay, so remember the fit, since we are still talking about regularization, we're still talking about regression and least squares regression. The fit is measured like this. And then I have regularization, which is lambda W 2-norm square. So it's the sum of the squares of the coefficients. And just to contrast things, we draw a line over here, right? Our regular least squares regression, which we have examined so far, was just minimum of x transpose W minus y 2-norm square. Okay, and remember that in this case, what was our solution? The solution was, the normal equations. You can take the gradients or you can do the geometric analysis, which is x transpose W star is equal to x times y. Right? So it's equal to W star, which are the coefficients being equal to X transpose inverse times XY. Okay. Well, what is the solution over here? Okay, well, I'll leave it as an exercise. You can again mimic what I did for least squares regression, and it's not really complicated at all, right? And what you get is if you take the gradient and you set it equal to 0, you'll see that the resulting equation that you will get is basically very similar, except lambda makes an occurrence, and lambda makes an occurrence in this way. XX transpose plus lambda I, W star is equal to XY. Okay, so you can see that, there is seemingly not much difference. There's XX transpose here, there's XX transpose here, but here there's a lambda I, and as a result, my optimal coefficients are XX transpose plus lambda I inverse times XY. And if you think about it, right, what's happening over here is that earlier this inverse value, remember as I was going from m equal to 0, 1 through 9, these values were actually becoming very big. So W star was getting very large. And what ends up happening is that when you do lambda, right, it dampens things. And you're taking the inverse of not XX transpose, but XX transpose plus lambda I. Any questions? By the way, if there is a question that comes up on the chat, because many times I don't pay attention to the chat while I'm lecturing, somebody can just just say, hey, there's a question on the chat. Okay. There's no question right now, so let's look at now how these compare. Okay, so now in least squares regression, we saw last time that prediction on training data. Okay, so remember the prediction on training data is always going to be X transpose W star. Okay, and that's just going to be X transpose times W star is given over here. So it's X transpose inverse XY. Similarly over here, the prediction on training data is X transpose W star. And now I have X transpose and my W star is XX transpose plus lambda I inverse times XY. So very similar, right? But now let's see how the singular value decomposition can actually help us in analyzing this. Okay. Not talking about computation, but just to analyze what is going on. So remember we did this last time also. So we did X transpose. So let's look at the SVD of X transpose. Okay. Then if we do X transpose is equal to V sigma U transpose U sigma V transpose. And this is equal to V sigma square V transpose. And if I look at XX transpose inverse, that's going to be V sigma minus 2 V transpose. Okay. And then when I want to look at the prediction, which is X transpose W star, which is X transpose inverse X transpose W star, that is going to be, what is that going to be? Sorry, I think I may have, let's see, sometimes I get tripped up between the transposes. So it is X transpose and X over here. Okay. So it's U sigma V transpose. And then from here, I have V sigma minus 2 V transpose. Remember, I'm actually just repeating things from last time. Okay. And then I have V sigma U transpose. Right. And what happens is that this gives me identity. This gives me identity. So I get U sigma minus 2 sigma U transpose, and that's equal to UU transpose. Okay, with UU transpose times, so again, I made a typo over here. This was Y over here. Okay, so it's taking the given data, the given training data, you form a vector, and then you project it onto the space, the range space of X transpose. Okay, so this is, I can also write this as summation of UI transpose Y. Okay, I equal to 1 to T plus 1, where D is the dimensional. Okay, and this is orthogonal projection onto range space of X. Let's look at what happens in the case of ridge regression. Okay, so let's do something similar, right? So again, my X transpose is equal to U sigma V transpose. Same thing as before. Again, I have, now remember that in this time I have XX transpose equal to V sigma square V transpose. And what is XX transpose plus lambda I? So earlier I had XX transpose inverse, okay? But now I actually have XX transpose plus lambda I inverse. Okay? So, well, I can actually write this as V times sigma square plus lambda I, V transpose. And that's because V is n by n, it is square, right? And that gives me the identity. So I can write lambda inside. Okay. Then I look at X transpose W star, and I get X transpose X transpose plus lambda I inverse times XY. So very similar, right? Except instead of XX transpose inverse, I have XX transpose plus lambda I inverse. And then I can just substitute from here, right? So XX transpose plus lambda I inverse is equal to V sigma square plus lambda I V transpose inverse of this. And that's just equal to V sigma square plus lambda I inverse of V transpose. okay? Because V transpose is the inverse of V, okay? And then my prediction is X transpose W star, right? So I have U sigma V transpose, V sigma square plus lambda I inverse V transpose, V sigma U transpose. Bear with me, because finally when we come to the end, we will actually kind of see quite a beautiful explanation of what bridge regularization is doing. But we have to kind of go through the algebra. Okay, so again, this is equal to identity, this is equal to identity, and what you get is U sigma square plus lambda I inverse times sigma times U transpose. Okay, so and earlier, remember that when lambda was equal to 0, then these would have all canceled out. Okay, but this time lambda is not equal to 0, right? So things actually don't cancel out. So what is this matrix? This matrix, what is this? If you think about it, remember it's a diagonal matrix. Sigma has, the little sigmas on the diagonal. So here is the first element of this matrix. It's sigma 1 square. That comes from this sigma and this sigma. And then since it's the inverse of a diagonal matrix, the elements of the diagonal elements of this matrix are basically just the inverses of the corresponding diagonals. So it becomes sigma 1 square divided by sigma 1 square plus lambda. The 2 element is sigma 2 square divided by sigma 2 square plus lambda, and all the way. Okay, and it's sigma d square divided by sigma d square plus 9. So it's a diagonal matrix, zeros on the off diagonals, okay? And if I want to get a similar representation over here as here, right? If I take this, then what I get is that this is equal to summation of I equals 1 through d plus 1 sigma I square divided by sigma I square plus lambda times ui transpose. And I guess instead of d still go d, then this goes still d plus 1. Now, what can you say about this? This coefficient, remember when lambda equal to 0, it's equal to 1 when lambda equal to 0. Okay? But in general, it is less than equal to 1. It's equal to 1 when lambda equal to 0. As lambda becomes bigger, the denominator keeps on becoming bigger, and it actually starts going towards 0. So let's look at that again. Okay. So if my sigma I square, which is this ith singular value, is much bigger than lambda, then what happens to this number? Sigma I square divided by sigma I square plus lambda. Okay. If sigma I square is much bigger than lambda, this will be nearly equal to sigma I square divided by sigma I square. And so it'll be is nearly equal to 1. In particular, if lambda equal to 0, right? But now let's see what will happen. If sigma I square is much smaller than lambda, then I have sigma I square divided by sigma I square plus lambda. And this will be approximately equal to, so remember sigma I square, that'll stay in the numerator. And sigma I square plus lambda, when sigma I square is negligible compared to lambda, is going to be lambda. And that is going to be nearly equal to 0. Okay. So what ridge regression does, and we are able to only do this analysis by looking carefully at the singular value decomposition. What ridge regression does is it shrinks the small singular values to 0. Okay, any questions so far? I think many people should have questions, right? Okay, so just to repeat the difference, what ends up happening over here is you have this matrix X transpose. It has D plus 1 singular values, and they can vary in magnitude. The first singular value can be much larger than the D plus 1 singular value. In particular, if X transpose is not full rank, suppose the features are identical, right? Then sigma D plus 1 could actually be equal to 0. But what linear regression does is it actually eliminates sigma over here. Sigma I is not over here. So it treats each singular value to have the same importance. And it basically just does a projection on the entire space. But what can happen is that what can end up happening is that, that some of these singular values could actually be very small. So when you take the inverse or minus sigma minus 2, this could actually be very big. Okay, so the coefficients can actually blow up in the prediction. And what ridge regression does is that the large singular values, when sigma I square is greater than lambda, then it basically does the same thing as ridge regression, as least squares regression. It basically keeps them at 1.
Hey Inderjeet, there's a question on the chat by Rishabh.
Yeah, go ahead. Rishabh, you can feel free to ask me a question.
I just wanted to clarify on the right side when we were going over the equations for ridge regularization, what happened to the y term? Did that get canceled out somewhere?
Oh, thank you for bringing that to my attention. I'll just add that back in.
Oh.
Is that good?
Yeah, thank you.
Yeah.
There's
Okay.
another one by me.
There's another one, yes. Can we say small? So Mohammed, can we say small singular values are noise in the data and regularization leads to not overfitting to the noise? Yeah, I think that's kind of a valid way of looking at it. Does that answer your question, Mir? Yeah. And sometimes remember that we are, when you're running on the computer, you can't represent a real number exactly, right? So you represent numbers as floating point numbers. Whenever you do an operation, there's some error in it. So many times when you get these small values, you cannot actually trust them. And what ridge regression is doing is in some sense kind of eliminating them, but in a smooth way. So notice that, here's another thing we could have done, right? What if we had done the following, that, so this is shrinkage. What if we had done some hard shrinkage? Let me clarify what I mean. What if I had said that, I'll take the sigma I square as is for I equal to 1 through, let's say, k. And then I will take sigma I square and replace it by 0 for I equal to k plus 1 through d plus 1. I could have done that also, right? What I've done above is like, it's a smooth change. But I could have done this, and that all that is saying is that I'm actually now using the k truncated SVD. Because if you look at it carefully, then it'll just be that you're taking the k singular values as is, and you're truncating the rest of them to 0. Okay, and that actually is also kind of a valid thing that you can try to do, right? I mean, you can. I think ridge regularization is kind of more accepted in the language of modern deep learning. It's sometimes called weight decay. Okay, but you could potentially also set the small singular values explicitly to 0, whereas here they are kind of being gradually set to 0. Okay, and remember, and for example, over here, it could happen that all the singular values are large, in which case, it won't make that much of a difference. Okay, so I think this is, very, most people, when they look at ridge regression, right, they see this. Okay, and it's kind of a good motivation, and you can say that, you don't want your model to be too complex. You don't want your W to be small. But then when you kind of look at the solution, this
There's
is,
another question by Ritesh.
yeah, let me finish. So you basically, get this. The solution is this. And what it says is to solve for this minimum W, that's equivalent to saying that you're going to take the small singular values and start ignoring. Okay, what was the question by somebody? Ritesh, yeah. Is there a property? Oh, yes. Ritesh, you cannot speak, but that's the definition of SVD, right? So if I go back to my previous lecture, when we talked about the SVD, we arranged them in this way, right? That sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma n. So they are increased in decreasing order. So does that answer your question, Ritesh? I guess you said you can't speak, but I'm hoping you can say yes. You're just moving single values. Well, okay. So I'm not sure what you are asking, Ritesh, but ridge regression does not just remove the small singular values and set them to 0. Ridge regression does exactly what I gave over here. It's essentially taking the ith singular value and replacing it by sigma square divided by sigma square plus lambda. And that has the property that when sigma square is very large, much bigger than the regularization coefficient lambda, then the sigma square will be essentially, what you're doing is that coefficient is 1. And when sigma square is very small, then it is sigma square divided by lambda, which will tend to 0, but it's not exactly 0. An alternate way could be to do this hard shrinkage, where you set the small singular values to 0. okay? And you keep the large singular values as is. That's also a way to do things, but it's not the same as ridge regularization. And if you now think about doing this on the computer, right, to do hard regularization, you actually need to know the SVD. To do ridge regularization, you don't need the SVD. All I'm doing is I'm showing an analysis. So for example, if you want to solve this problem, then you don't need to find the SVD of X. You can actually do it using, Pulaski decomposition, QR decomposition, and so on, or you can actually use an iterative algorithm to do the solution. Okay, and I think you'll see in the first homework that we'll assign on Monday, when you look at this collaborative filtering problem, which is like, let's suppose you're given like a whole bunch of movies and ratings by users of movies, then and you then want to predict the rating of a movie by a given user, then you will see that the algorithm that you will use in your homework will not need you to compute the SVD, because the SVD finally is quite an expensive computation to do. So here, what it's doing is it's really helping us to understand what is going on. But you typically will not solve this problem by computing the SVD. So that's why doing this hard shrinkage is something that is much more expensive, whereas ridge regularization is much more, it can be done without the SVD, but it can be interpreted as doing some changes to the singular values. Okay, does that clarify things? Yeah. So that's actually a pretty important point. Huh? So the singular value decomposition is a very good tool, but it's actually quite expensive. And when we talk about very large data sets and the analysis of that, typically you don't compute it. You will not be able to compute. Okay, so let's look at another view of ridge regularization. Okay, so ridge regression. So far we've said, minimize X transpose W minus Y square plus lambda times 2 normal square. Okay. This problem is actually a little equivalent to the following problem. Okay, so to the following. Okay, so take the same objective as least squares regression, but then you say, I don't want my coefficients to grow too much. So I'm actually going to put a constraint that my W2 square should be less than equal to C for some C. So over here, the trade-off between regularization and fit to the data is lambda. And over here it is C. Okay. So the following is a constrained optimization problem. Okay. So this problem, which is typically how ridge regularization is posed, is equivalent to this constrained optimization problem. And the reason I'm mentioning the last part is that we can geometrically kind of try to understand what is happening, right? And it'll actually help you understand a different kind of regularization, which is when we don't regularize by the sum of squares, but we regularize by sum of absolute values. So instead of L2 norm square, we can actually regularize by the L1 norm, which leads to what is known as the lasso, which you might have heard about. Okay, so geometric interpretation of this above constrained optimization problem. Okay, so what you can show is that if I look at this function, our least squares function, then it actually looks like the following. Okay, it's if I look at the contour map or level sets, and I'll explain what level sets are. Okay, so if I look at, okay, so level sets are where FW is a constant. Okay, so the contour map is actually something like, looks like this. These are ellipses, and I'm not showing that over here, but it can be shown. Okay. And this, each of the contour maps corresponds to FW equal to C1 for some particular C1. Okay. And this one would correspond to FW equal to C2, and C2 is less than C1. Okay. And this value over here is going to be FW equal to 0. So this is the minimizer. This is the d-squared solution. And now if I look at my constraint set, right? So this is my constraint set, right? And if I look at that, okay, if I fix a particular C, I guess I should have used a different notation. Let's see. Maybe I'll change this C to, okay. Okay, let me just say R for radius for some R. Okay. So this is typically going to be like R is the radius. And what I'm saying is that my X norm of X square is less than or equal to R. And what I'm saying is my constraint set is this. I want only, sorry, I wrote W X, but it's W. The only W's that I want are actually within this. So the solution of ridge regularization, or the constrained version of ridge regularization, is that you basically look at the level sets, and the first time the level set meets the constraint set, okay, that is the ridge regularization solution. Okay, so this is another interpretation of ridge regularization, right? You're minimizing f of w. It'll be minimized over here if you're just looking at f of w, which is the least squares problem. That gives you the least square solution. Okay, but that's not what you want, because this w magnitude might actually be very far. It might be very far from the origin. As a result, these w values could be very large. you want these W values to be small. So you have this constraint that my W values cannot have sum squared to be bigger than R. They must be less than or equal to R. So geometrically, the minimum value of this constraint in optimization problem is when the level sets first hit this R radius R sphere. Okay, so that is an interpretation of ridge regularization. Any questions about that?
So is there a relationship between R and lambda?
What's that?
Is there a relationship between R and lambda?
Yeah, so basically for every lambda there exists an R, but there's no straightforward relationship.
Thank you, I see.
Yeah, but basically, you can either work with R's or you can work with lambdas, right? And solving like a constraint optimization problem is generally numerically a little bit more difficult. So people, whenever they solve it, they really look at this version of the problem. Okay, and then they typically, will use either an iterative, depending on the size of the problem. Either they'll use a very an iterative algorithm, it's very large, or they can use the Koleski decomposition or even the SVD. Okay. But the important point to note is that this can be represented as this is equivalent to a constraint optimization problem. And one of the reasons I'm sorry, go ahead.
I just said thank you. Got it.
Sure, yeah. And one of the reasons I'm talking about this is that there's another kind of regularization that is actually very popular, or maybe used to be popular, is called lasso. Okay, and lasso has the following objective. Same objective as least squares regression in terms of the data fit. So X transpose W minus Y 2 norm square. But now the regularization is changed to be the 1 norm of W. So seemingly like a pretty innocuous change, right? Instead of some square of sum of the squares of W, we are penalizing the sum of the absolute values. Okay, so it's basically 1 norm of W instead of squared 2 norm. People use this. And one of the reasons actually people use this is the following. That lasso many times leads to a solution with sparse W. Okay, and what do I mean by sparse W? That is coefficient vector with many zeros. And you can think of that as, it's basically a more parsimonious model. Parsimonious. Right? So remember that I'm taking a linear combination of the D features, right? D could be very large. In modern problems, D could be as large as 1,000,000. So what that means is that you now have a coefficient of 1,000,000 features. Okay, but somebody can ask, okay, can you give me a solution which has still a good solution, a good fit? Can you give me a solution which has lesser coefficients? It's a more interpretable model. So what happens is that the lasso results in a more parsimonious model. And why is that? Okay, and now we can see that if I look at lasso, okay, I can think of it as being equivalent. Actually, let me say that it's equivalent to the following constraint optimization problem. The same thing that we did before, I'm following that. The following constraint optimization problem, which is minimize W x transpose W minus Y squared such that, what is the constraint now? That norm of W, but the one norm of W is less than equal to R. Now, if I look at if I draw it geometrically, what is the norm of W less than equal to R? I wonder if I did that before, right? So for example, if I go back to the linear algebra review, when we talked about different norms, oh yeah, look, I did that here, right? Norm of W is less than equal to 1 is this set, right? Because this has boundaries 1, 0, 0, this has corner points as 1, 0, 0, 0, 0, 1, and so on. And in between, these are straight lines. Whereas the two norm, the constraint set is a sphere. So this actually has corners. This boundary has corners, and that's why it'll actually give sparse solution. Okay, so this constraint set will be sorry, my drawing is not the best, but it's going to be norm of W1 is less than equal to. Okay, and given my data, suppose it's the same problem, I'll basically get something like this. My f of W, right? So if I draw the level sets of that, it's going to be something like this. And then the solution will be the first time it actually hits. And because this has corners, you can see that the solution is here. This is the lasso solution. Is usually sparse. Now remember, I'm drawing this in two dimensions, but this is happening in D dimensions when there are D features. So D is a million, your like D-dimensional space. So it's not going to be like only one variable is negative or is non-negative, but there may be many variables, okay? And remember, there is the regularization coefficient, right? So as you increase lambda, right, that basically means that you are decreasing R, right? And you will basically get sparse solutions. Okay, any questions about that? Sometimes it's also called the contour map. You've probably seen these kinds of maps when you do hiking and so on, right? This is a convex function, so it's like this, and every level set is a ellipse. Okay, any questions for me? Okay, so let's recap. We started this course off with talking about regression. We looked at least squares regression, the sum of the squares. I think right in the beginning, there was a question like, why are we looking at sum of squares? And you've seen that we've developed kind of a, some really nice intuition. And one of the big reasons why we use sum of squares is because it's, in some sense, good to analyze. It's easy to analyze, right? So then we realized that, hey, we need some linear algebra for this. I did some linear algebra review. Then we came back and said, today what we saw is that, hey, least squares regression by itself is not a good predictive method because it can overfit. And that principle is very true of machine learning in general. So this is a particular example where you don't want too complex a model that fits your training data exactly, because that leads to overfitting. In the context of regression, we saw that we can prevent overfitting by penalizing the coefficients that we have, the coefficients W. Ridge regularization is one way to do it. And you can think of, that has the interpretation when we look at the SVD that, you're kind of shrinking the small singular values towards 0 and the large singular values towards 1, but it's not doing like a hard operation on them. And then we saw that there's another regularization method called lasso, okay? And I kind of gave you some intuition as to why that leads to a more parsimonious or a sparser model where the coefficients have many zeros. As a result, the predictor is only using a few of the D features. Okay, so with that, we are kind of coming to the end of how much regression we will do in this course. I will, on Monday, I will give a lecture on collaborative filtering, which is, recommendations by, like a very important problem these days, right? Which is collaborative filtering, recommendation algorithms, and so on, right? So we will look at one particular way of doing collaborative filtering or recommendation. And that, back when the Netflix price happened was actually one of the leading methods. I'll talk about that method and see that that naturally basically is a regression problem. I'll do that lecture on Monday, give you your first homework on Monday that will involve programming, right? And then once I finish the collaborative filtering lecture, then from next week onwards, Wednesday, I'll start talking about classification, okay? Where the variable to be predicted is not real, but is categorical. Predict whether, for example, an email is spam or not. Okay, so that's what is coming up in the course. Okay, so with that, we are at the end of this lecture. Any questions on the material that we've seen so far?
Excuse me, you mentioned that lasso is not popular anymore. Is there any reason for that? A specific reason?
When I say lasso is not popular, I mean, basically everything has been taken over by deep learning. So,
I
uh,
see.
so,
And weight
so
decay is a more natural way for doing it.
yeah, weight decay is like, just naturally comes up in deep learning. And then if you try to get sparse solutions, you have to deal with the fact that it's not a differentiable function and so on. So typically, I haven't really seen much use of lasso kind of regression in deep learning.
Thank you. Got it.
But it's still very important. It's good to understand. And maybe there are some cases where we kind of, may want to look at L1 regularization, even in, deep learning applications.
Yeah, I think interpretability is still a big issue. Right?
Well,
So
that's a huge issue with, I mean, if it's a big issue with ridge regression, it's an even bigger issue with deep learning. But I think generally what we have seen is that the quality of the approximation people care more about than interpretability. So in particular, people generally might care more about, the goodness of a recommendation algorithm than being able to interpret it.
yeah, makes sense.
I
Thank
think
you.
that's just true. Okay, I see some comments. Got it. Thank you. Thank you. Okay, good. So that ends this lecture, and I will see you on Monday. Bye.